Okay. So, good evening, everybody, and good morning to Professor Ron from US and Professor Ron Ziemian. I would like to welcome all of you for the fourth keynote session of the first international conference on steel structures held at IIT Hyderabad in India. And I would like to introduce you, the keynote speaker, to all of you. And Professor Ron Ziemian is a full professor in the Department of Civil Engineering at Bucknell University, USA, and he is the editor-in-chief of Journal of Constructional Steel Research, one of the leading journals for structural steel. And his research interests include advanced methods of computational analysis towards stability of metal structures. The title of his talk is Structural Stability, Letting the Fundamentals Guide Your Judgment. So the talk will be for 25 minutes, followed by 5 minutes of question and answers. Thank you very much, Ron, for accepting our invitation and gladly presenting it. The floor is yours now.
All right, very good. First, one quick check. You can hear me okay?
Yes, I can hear you okay, and your slides are visible.
All right, great. All right, well, let's get started. Good morning from here, but to you, it's good evening. I hope this presentation finds you all healthy and enjoying a wonderful conference. Many thanks to the Indian Structural Steel Conference Organizing Committee for allowing me to present as a keynote speaker. It is my honor and absolutely my pleasure to do so. Many more thanks to my good friend and professional colleague, Dr. Madhavan, for not giving up during such a difficult time and continuing to host this great event. There are so many wonderful presentations. Unfortunately, with the time difference, it's very difficult for me to attend many of them, but I really so much wish I could be there at Hyderabad with all of you. So one of the first questions I often get asked is, where is Bucknell University? We are a small university of 3,500 undergraduate students, so we don't have graduate students, master's or PhD students. We are located in the center of Pennsylvania, and here is what our campus looks like. Again, very small on a sunny summer day. But if you were here today, you would be very cold, as it is -3 degrees Celsius. Please, if you're ever in central Pennsylvania, look me up, come visit. It would be great to host you. So as Dr. Madhavan has indicated, the title of my talk is Structural Stability, Letting the Fundamentals Guide Your Judgment. It's not a very technical talk. So I apologize for that, but maybe it's a good thing given it's starting to become late in the evening for you folks. I will be focusing on fundamentals and judgment as they impact your thinking towards structural stability. So it's great to be here, and let's get started. So first, I'd like to begin with those fundamentals. And I know the audience is full of brilliant engineers out there. I do not intend to insult anyone here. I just want to sort of, maybe for many of you, remind you of a few things. But a lot of times when I get questions about structural stability, I often find it weaves back to the fundamentals. So we'll take a few minutes and go through those. The first one, force follows stiffness. And so let's begin by thinking of a system in which all the components are in series. And this is not a good situation in design. As you are aware, stiffness in series degrades horribly. In fact, the system stiffness, and don't think of this, my example is just a few bars here and some connections, but you could think of this as an entire building where the components are in series. And the system stiffness is actually much smaller than any one of the individual stiffness of the components. And so many times in structural stability, when I'm faced with questions, the engineer will say, well, we had this bracing problem, okay. And then I look and see all the braces are in series. And I said, okay, and how did you try to fix the problem? And they said, well, what we did is we added one huge brace to it, and that one was also in series. And I just, oh no, you're even making the problem worse. And this is a bit baffling to them at first, because they They think adding more steel is going to solve the problem, where in fact, this is a situation where adding more steel, it does not, it actually produces more problem than helps the problem. Now, the counter to this is to put your components in parallel. And this is a very good thing. So once things are in parallel, the stiffness is additive. So try to always go in this direction. So again, as you're looking at structural systems and you're providing more and more components, emphasis on putting those components in parallel. The other nice thing about having the components in parallel is it provides, of course, alternative load paths should something go wrong. And that is not the case when a system is made up of components in series. And so just keep that in mind. The next one, quickly, the basis for every structural analysis. Well, there are three fundamentals here. Every structural analysis or stability analysis is based on your equilibrium equations. And that would, of course, be a balance of the internal forces and moments with the external applied loads. Compatibility equations, which are often forgotten about, but again, another balance or making sure that the displacements and rotations at the end of all the components are in agreement. And honestly, between having your equilibrium equations and your compatibility equations, you have more than enough equations to solve any structure's problem. The issue is that some of your equations are in forces and moments and some are in displacements and rotations. So what you need to have is some way to get them all of your equations in a common set of units. And that is how we would use our constitutive equations. So I tend to think of our constitutive equations as the translators. The reason I bring this up is in structural stability, we're often asking ourselves, was the analysis a geometric linear or nonlinear analysis? And that the answer to that question, was the analysis second order? The answer to that question comes from a second question, and that is, were your equilibrium equations and your compatibility equations formulated on the undeformed shape or the deformed shape? And if they were on the deformed shape, then you are doing a geometric nonlinear analysis that you probably wanted to do. The next thing on stability in nonlinear analysis would be material nonlinearity. And the only place that you're going to be able to pick that up is with your constitutive equations. And so that's why I wanted to hit that one. So whether you're dating back to 1750 with Euler and deriving the column buckling equation, or moving all the way forward to today's amazing computer analysis capabilities, no matter where you look, whether you're in the code or in the derivation, almost all of them are based on equilibrium, compatibility, and constitutive relationships. So make sure we don't forget that fundamental. Another one is superposition, especially when it comes to structural stability. And again, it's very tempting to use. It's wonderful. The problem is it requires a linear response. And when you're considering conditions or design conditions for serviceability, you most likely have that linear response. But when we start to look at ultimate strength design, instability, things are most likely going with a geometric and material nonlinearity, and superposition is not permitted. The last fundamental I want to focus on is you really need to have a good feeling for the behavior of steel structures. And just some high points there on material behavior and stability. So with regard to material behavior, I think we're all well aware that steel has an amazing amount of ductility. And in the upper left of this picture here, I'm showing you what most of us envision as a stress strain diagram for a steel coupon. The thing is that whenever we draw these things, we never draw them to scale. And so we don't really fully appreciate the ductility of steel unless we draw them to scale. So what I'm going to use down at the bottom here is a football field, an American football field that's just about 100 meters long. And to put things in perspective, I just wanted to show you where some of the key points are. And that is the first meter of this 100-meter football field or 100-yard football field represents the elastic zone. And it's within that first yard or so that we actually do most of our design. But we do have the ability to yield the material. And before it even strain hardens, we can get, say, 10 yards, 10 meters down that football field. But steel has so much ductility that we actually don't get fracture until we go the full 100 meters to the other end of the field. So if we were to plot this thing at scale, it would most likely be very difficult to even see the elastic range, even though that's where we're doing most of our design. Unfortunately, just because we have an amazing, a steel has an amazing amount of ductility, it doesn't guarantee our components will have that amazing ductility. So there is a reason that this graduate student is smiling. That connection has been designed quite well, and it is able to take advantage of the ductility of steel. And so keeping in mind then that we can use a ductile material and not get ductile performance. So we do have to work at it, and a well-proportioned steel connection will provide you that ductility. And if you look at that connection, you can see a massive amount of yielding taking place, no fracture, all good things. Some more thoughts on designing with steel. Steel has an amazing strength to weight and stiffness to weight ratios. And these are great things for us to take advantage of. Steel can be competitive in pricing. So what often happens when we design steel structures is we end up with very slender systems, very slender members, and slender cross sections. And as a result of this, one of the primary factors that we need to design for is indeed structural stability. So when I just describe designing steel structures, in my mind, I think connections, 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 and also make sure you design for stability. I'm not going to be talking about connections today, but focusing on structural stability. To many of us, structural stability sort of comes down to thinking about buckling, all right? And I wanted to use either the flexural buckling of a steel column, as you're seeing in the lower left of this figure, or the lateral torsional buckling of this beam that I'm showing in the upper right figure. In both cases, or even if we were looking at a system, we could use the plot in the middle to describe two fundamental approaches to buckling. The first would be what I'll call bifurcation theory, shown in the red curve. And that is, as we plot the deflection, either the flexural deformation or the lateral deformation in that beam, for a bifurcation theory, there is no deflection, according to our theory, until suddenly the thing buckles, and then we have unbounded deflections. The other possibility would be what's shown in the green curve, and that would be to approach the problem thinking more of instability theory. And that is, as the load is applied, the structure starts with some type of an initial imperfection. And at first, not much happens. But then as the stiffness starts to degrade, that initial imperfection will start to grow. It will cause the stiffness to further degrade. Eventually, we'll get some yielding. Yielding will mean probably more bending. And eventually our deflections will become quite large, as the green curve is showing. And in many cases, the instability theory will match what you get in bifurcation theory. But there are advantages to using the instability theory approach as opposed to the bifurcation theory approach, and that's what I'm going to try to show you. Quick note, as I said, my title is Fundamentals and Judgment. So let's just hit the judgment thing for a minute. What I'd just like to encourage all of you out there, the designers, the educators, is just don't give up, all right? Don't give up on judgment. Embrace every opportunity to exercise your judgment. Note that it has to be constantly developed. So we don't learn it in school and, all right, we've got it all. But constantly also question your judgments. All right? What were the assumptions made in this particular design, especially with regard to stability? Are you satisfying equilibrium and compatibility? And please note that if you remove judgment from the equation, then you're no longer a structural engineer. A computer could easily replace you. So judgment is key and will always be key to our profession. Always have conversations about your designs, especially on their way to the foundation. Talk in terms about ultimate strength failure modes. Of course, you design the structure not to fail, but what if it were to fail? How would it fail? Okay. Many times engineers, designers forget to just simply plot deformed shapes and moment diagrams. As a consultant, that's often where I start. And in many cases, that's all I do. Plot the deformed shape. The engineer realizes what happened. But unfortunately, I still get to bill the client for several $1,000s for my consulting fees. And all I really did was bring their attention to plotting the deformed shapes. Maybe not several $1,000s, but at least a few hundred. Finally, keep in mind that judgment comes with years of experience. So if you've been at this for a while, please make sure you become a mentor to the younger generations. And if you're from the younger generation, please let yourself be mentored, all right? Open your eyes up and listen to those people with all of that experience. So those are my thoughts on judgment. All right, let's have a look at designing for structural stability next. In the early 2000s, I had the pleasure of serving on AISC's committee that developed or redeveloped how to design for structural stability in our AISC specification. And our small group really looked backwards at many reports, and one of them, a 1980 report by Iflin and Bernstein, really defined things for us, and they listed all of the factors that tend to influence frame stability, and they collected them in groups of geometric effects, material effects, and load effects. And so when we went and rewrote the AISC specification, the section, the chapter on designing for stability, we wanted to be much more transparent. And what we put up front was precisely those, and they've become known as sort of AISC Chapter C's Big Five. What they basically are is your stability analysis has to include pertinent deformations. Many times they're just flexural deformations, but they could include axial deformations, deformations due to the connections, deformations due to shear. Whatever those deformations are that may have a significant impact on the results need to be included. And how do you know if they have a significant impact? Well, as you start to write your equilibrium equations on the deformed shape, how much of an impact do they have on equilibrium? And speaking of which, you should be writing equilibrium on the deformed shape. That is, you should be considering second order effects, geometric nonlinear effects. Other factors involved that you should be considering are initial geometric imperfections, story sway effects, member imperfections as you see fit. Keep in mind that as we reach the ultimate strength, we're going to have a loss in stiffness due to partial yielding. So you need to think about how that will be included. And that loss, that partial yielding can be accentuated by the presence of residual stresses. And then, of course, there's a possibility for variations that can occur. Now, when we went on, we said, look, any method for stability design is acceptable, but we did provide two, the effective length method and the direct analysis method. So I'd like to review those. So if you put things back to that slide I showed you previously, the effective length method, which has historically been around forever, really lends itself to bifurcation theory. The new person on the block within at least the last 20 years is the direct analysis method, and that is much more based on instability theory. So for an engineer to transition, an older engineer, from the effective length method to the direct analysis method, it really required them to have a change in thinking of bifurcation concepts to sort of instability concepts. In general, and probably some of the previous speakers emphasized this, is that the whole concept of the direct analysis method is that by directly modeling effects known to impact the system or the members directly within your analysis, by covering them there, you are granted simplifications in computing the design resistant terms. So that's just it. The more you invest up front, the easier the design process can be. So AISC has probably three direct analysis methods. The first I'd like to let you know about is that if you directly is the most simple one, and that's provided in the body of our specification, and it is based on an elastic analysis. And so if you directly model the pertinent deformations, the stiffness and load distributions, initial system imperfections, right, not member, but initial system imperfections, and you account for yielding in some way, we use a 0.8 on top, then you are granted a simplification in which the compressive strength of the member can be braced simply on the unbraced length. So your K factor, your effective length factor, can be taken as 1. In 2016, we went a little bit further and revised, and this is in our appendix designed by Advanced Elastic Analysis, that if you invest a little bit more heavily in the analysis, in the rigor of the analysis, and you also include member imperfections, then you can actually move from going to the compressive strength being calculated as the cross-section strength, where member instabilities and system instabilities are being picked up by the analysis. So it does seem a bit strange that with each passing method, it seems that the compressive member, the design strength of the compression member, is gaining. And so I just wanted to show you that really all of the methods, the effective length method, the direct analysis method, or the advanced direct analysis method, all of them are elastic methods. And it is shown in the lower left in red there. Of course, as you move to the nominal strength in compression is increasing. But at the same time, what's happening is in the blue there in the upper right is you're including more effects. And with more effects, you're getting more or larger moments and larger moment demand. So there's a trade-off in which you gain strength and compression, but you give up or you have higher demands. So the trade-off often results in very similar designs. The final method, the more advanced method, perhaps both Kim Rasmussen and Leroy Gardner has spoke about these, is design by advanced inelastic analysis. And here you go all in. You directly model the yielding, the initial imperfections, the member. You have a very rigorous analysis. And what the simplification is you actually just get to move away from the specification design equations. You still need to satisfy the intent of the provisions, but you're relying now much more heavily on the analysis. And the really nice thing here is you get to go beyond the first plastic hinge and actually take advantage of the inelasticity that will occur before a structure reaches its limit state of strength. I've got a sliding scale here to sort of show you how things can move. On the upper part of my scale, looking at the top, is how prescriptive equations do you want to rely on? Do you want to rely heavily on them to the left or less on them to the right? And then in counter to that, on the bottom part of my scale for any given design situation is how much do you want to invest in directly modeling the effects? Small amount will require very specific equations. A large amount of modeling, much less reliance on the prescriptive equations. So for a structure like the one you're looking at here, the system is orthogonal. It's a pretty straightforward design. And so most likely an engineer would use either the effective length method or the simple direct analysis method, rely on the specification equations, and just provide a small amount or a limited amount of direct modeling of those effects impacting stability. On the other hand, when you get to more complicated structures like the one I'm showing here, for example, that airport terminal that you're looking at, it's constructed with tree columns. So it's not exactly clear what is the unbraced length. Do you use the entire tree? Do you use the trunk? Do you use the branches? What's going on here? And equally, that could be applied to that arch system down below. So the engineer needs to start scratching their head, and maybe it is time to think more advanced. They could still use an elastic analysis, but they would need to model, say, the imperfections. And I think they could come up with good designs on that approach. And then there's the all-in again, designed by advanced inelastic analysis. And a case study where this was done was a building that was designed for Harvard's campus up in Boston, Massachusetts, or Cambridge, Massachusetts. And you can see the building on the left there, and it was required to have a large open atrium, but the engineer needed to provide some columns, and the architect did not want anyone to be able to see those columns. So what the engineers did is they used very heavy, wide flange sections, and they turn them sideways and they cut out the web. So if you look at the dash segment, approximately where the people start there, I've sort of tried to highlight one of those columns. Now, a column like this goes well outside the thinking of our column design strength equation in our specification. So here the engineers actually did use to design those columns, to design that portion of the system, and designed by advanced elastic analysis. So there are lots of examples where you might go all in with an advanced and elastic analysis. If you wanted to optimize material, maybe you're manufacturing many repetitive designs. Situations where the specification has limited guidance, like the one I just showed you. The system is complex. And many times what we're finding this advanced analysis being used for is when you need to sharpen the pencil. There was a design change or some type of retrofit work needed, and you were really trying to limit the amount of work needed. So you're stretching the limits. So lots of possibilities within AISC in our specification, in many of the specifications now worldwide, on how to design by this new person on the block, the direct analysis method, which is getting away from the very traditional effective length method. So I'd like to finish up on just some thoughts on the future of advanced analysis and design. I've spent most of my 40-year career looking at this topic. It started with my PhD work, and I continue to do it and contribute in that way today. So just some thoughts here. So I think the one thing that has taken place over the last 20 years or more, 30 years, 40 years, is this continuous revision on whose element is the best. So we tend to be looking at, on the analysis side, at the finite element model. I think what we're going to see is a dramatic shift, still on the finite element model, but on how the loads are applied to the structure and the type of loading we consider. So whether it be seismic loading, wind loading, or fire, I think we're going to see a lot more time history analysis coming forward. Something like a wind loads, many tall structures, not even tall, but relatively tall structures are designed using wind tunnel testing. I think we could take the pressure measured at those taps in the wind tunnel testing, bring them into our structural analysis model, and use that time variation to actually get a much more efficient design. When it comes to thinking about hardware and software, it's amazing where we are today and where we can be. So there is definitely the possibility, and we're starting to see it more and more now, on the use of nonlinear time history analysis. Now, in the late 1980s, when I was doing my PhD work on using advanced analysis and design, we dreamed of the year 2020. And we were just thinking how fast computers would be. Everyone would be using nonlinear time history analysis. It was a no-brainer. But the problem is, and what we found is, even as computers in speed of analysis software increased by thousands of fold, the structural engineering profession made a very interesting decision. And what they decided to do is, instead of focusing on the sophistication of the analysis, they decided to do much more of an exhaustive search on the number of load combinations they would consider. In the late 80s, early 90s, a design of a structure might consider 20 to 40 at most load combinations. The engineer would heavily invest on which ones to look at. Today, the game has changed significantly because they can now look at 400-600 different load combinations. They tend to work more in an exhaustive search approach there. What will happen in the future? I'm not sure. But I do think eventually you're going to reach this point of diminishing returns on looking at more and more load combinations. And it's at that point, which I think is very close now, you will identify, say, the 10 or 20 controlling load combinations and do a much deeper dive using much more sophisticated methods of analysis. And then, of course, where not only our profession, but many of the other engineering professions are going, and that is on the use of virtual reality, artificial intelligence, and big data. And this, for me, is very exciting. I really look forward to seeing what we do as a profession with these concepts. I can't think of the number of times that a steel frame, very similar, has been designed by a million different engineers at a million different design companies. What if the next frame being designed had big brother sitting on their shoulder or a big sister sitting on their shoulder, and as they went down a route they really shouldn't be, the software responded and say, you know, for the last 1,000 structures we designed that look very similar to this, you're about to make a bad decision. And that would be awesome. But I'm sure you can think of many other areas in which virtual reality, artificial intelligence, and big data is going to come forward. So I'm going to wrap up here and just sort of say what I've tried to do is focus that it really all starts with the fundamentals. So make sure you don't leave those fundamentals. They influence your intuition. You get them with continuous education. You should be able to look in codes, specifications, and design guides, and you'll constantly see these fundamentals. You get a little bit lost. Things get a little bit covered up when you do a computational analysis. So you need to step back and not just say the computer got the right answer. You need to question those computer results. You need to plot those shear moment diagrams. And of course, so important to this and using those fundamentals is your experience, not only your own experience, but learning from your colleagues. So what I'd really like to do is make sure all of these things, from computer analysis to the codes to your experiences, they guide your judgment. Make sure computer analysis are not replacing your judgment. That's what you bring to the table, especially with respect to structural stability. So Dr. Madhavan, I thank you again for the opportunity to speak, and more than glad to take any questions at this time.
Excellent presentation, Ron.
Thank you.
I'm really thrilled because I just completed a course on teaching stability, and I went through all the equations and other things, and you have nicely put it in a nice manner to understand the fundamentals first. Which is what I tell my students all the time.
Great.
I think I really loved the way that you presented it. Fantastic, and I'll see if there are any questions from any of the audiences. I just wanted to ask you, are there any unsolved stability problems that are there still that some researchers should focus on? We have worked a lot on hot rolled steel from Lehigh University and Cornell and other places, but most of them are focused on hot rolled. Do you have any intuition on the kind of problems that researchers should focus on, stability related problems, especially in cold form steel, because stability is more of a concern in cold form steel than in hot rolled steel?
Sure. Well, thank you for your question. I think in the short term, I think we need to consider the impact, and it's going to be a very positive impact, but things will get quite interesting with respect to structural stability, or more interesting when we start to think about high strength materials. The high strength steels, what they tend to do is they tend to provide you with more slender structures, if you will.
Right.
And with a more slender structure, obviously structural stability is going to become even more important, that we understand this if we're going to try to take advantage of these high strength materials. So in the shorter term, and I can see these papers coming forward now in our Journal of Constructional Steel Research, more and more work being done on high strength steels. But at this point, the work that I'm seeing is a lot of experimental work, and and just getting down the basic parameters of, or anywhere from how much ductility do high strength steels provide, to what happens in a fire, or high temperatures, what happens after the high temperatures to these materials. So we're still pretty much looking at things from a materials basis, but the next step is, all right, now it is actually time to apply these. What what's going to happen when we go to design structural systems. Is it all the same, or are we going to see a lot more buckling and a lot more concern for that? So I think that's the direction that on the short term I would go. In the longer term, I think it was quite exciting, to see the work by Kim Rasmussen and Leroy Gardner. They have got their sleeves rolled up now, and they are thinking about, what do we do in assessing that ductility. And so Leroy's suggesting, we look at the strain demands. I totally agree. If you go all the way back to Euler and buckling and what we did from there, what did we do? We converted the buckling load to a buckling stress, and off we went. But if you actually reformulate that and you formulate it in terms of a buckling strain, the modulus elasticity is no longer in the equation. So just from Hooke's law, the E is out of there. And so these strain concepts and looking at strain start to become material independent. And whether you're looking at aluminum or steel or wherever you have timber, the buckling strains tend to be much more consistent, at least the elastic buckling strains. And so I think that's going to be really interesting to see where we go with that. And in the long term, like I was trying to say in the previous slide, what is going to be the impact of these full nonlinear time history analysis? A portion of the structure starts to buckle, but then 1/10 of a second later, the earthquake shifts direction and it unbuckles the structure. Did we destroy the structure, or is it still alive? What's taking place under these extreme events that we designed for? So just maybe a little bit longer answer than you were looking for, but I think those are sort of my general thinking of where things are going to go.
Okay. The reason I asked is that sometime back I had read a paper by Raida Bihode, who just passed away, regarding the high strength steel, where he was emphasizing the need to increase the E value. So he said that metallurgists have not come up with increasing the E value, remains the same regardless of high strength steel or low strength steel or medium strength steel. So buckling is all function of E value. And if the metallurgist can do something to increase the E value, perhaps even by 10%, that would be a great shift in that direction. That is what he said. And also, recently, 3 years back, I met him in Hong Kong, where he delivered a keynote that instead of high strength steel and normal steel, he said medium strength steel. He was propagating 450 MPa as the ideal material for construction. So,
yeah, well, I totally agree with you. It was a great loss to our profession when Dr. Professor Radar Bihove recently passed away. His work, I mean, even starting back with my PhD work, was based quite heavily on his PhD work at Lehigh University. The amount of material he covered, from structural stability through connections, through a progressive collapse over a person's career, was quite impressive. Yeah, no doubt about it. If you wanted to be the next billionaire, find out how to increase the modulus elasticity of steel by even a small amount of as 10%, and you will be that much better off. I do like your final points there, that there may be a point of diminishing returns on those high strength steels with respect to structural stability. But at the same time, we may need to be more clever in using high strength steels in connections where we could really take advantage of them, but the rest of the member not necessarily being high strength steels. And then, of course, you've got the whole world of composite design in the combination now of not only high strength steels, but high performance concrete structures. Yeah. So it's an exciting place to be in the world of structural analysis, design, etc.
Sure. Thank you very much, Professor Ziemian. I think there is one question that has been asked by a participant. Can you see the screen?
I cannot. Can you read it for me?
Yes. Notional loads are given to simulate initial geometric imperfection in direct analysis method. How reliable it is for a wide range of steel columns?
Yeah, this is an excellent question and one I very much appreciate getting. Again, for the broader audience, we use notional loads in many cases as a simple device to represent the initial imperfection or to represent the loss in stiffness due to some inelasticity. It's a fantastic method. It's certainly a lot easier than actually going in and distorting your finite element model to some type of an initial imperfection. The problem that I have with the notional loads is their definition, 0.002, whatever you've got of the gravity load, is heavily based. The notional load is heavily based on using an orthogonal geometry, a geometry in which the values are set at, and that is the columns and the beams pretty much coming in at right connections, right and 90-degree connections. And so when we came out with the direct analysis method, and those of you that look at AIC in 2005, when we talked in the chapter C or the appendix on the direct analysis method, and we spoke about how to handle geometric imperfections, the first thing we said was use notional loads. And the second thing said model them directly. And we changed the order there because we really wanted to be transparent in that the best way to do this is to actually model the imperfection. But given that most cases you do have an orthogonal system, it is acceptable to use notional loads and get there. But I do think as you're using notional loads, you need to, again, question your judgment there. If it's some, and these architects do go crazy. So if it is a more complex geometry, and you've got to make sure that that notional load is adequately handling the imperfection that could actually exist. So that would be my quick thinking is they're a good device, but they need to be used with careful attention.
Okay. There's another question from another audience. So, with the demands for more sustainable constructions becoming higher, okay, so as the dematerialization of the construction as a whole, how to deal with growing lighter structures in terms of stability?
Yeah, this is a great point. I get excited about that. I'm not afraid of slender structures. I think it's amazing. I think we have the tools. We've got to make sure we have our engineers properly educated and prepared to take on much more slender structures coming from the use of much less amount of material. I think what we will find is that as we go in that direction and we try to use less and less material from a strength side, we are going to be fine. We can solve that problem. We can design adequately. We can design these super light structures. What's going to happen is our structures also need to be serviceable. They need to function under everyday loads. We cannot have excessive deflections or vibrations. So in many cases, even in today's world, what is controlling the design is not the strength, but the stiffness. And when that becomes the issue, as much as I'd like to have a very slender structure being able to do this, it can work from a strength side. It's not going to fall down and hurt anyone. But unfortunately, we also have to function in it. And we've got to be clever about how to pull that off. Now, that's not to say it's impossible. We can have very slender structures that also perform adequately with respect to serviceability. And the trick to doing that is to introduce other mechanical systems like dampening systems or other devices. And so we've got to think about walking across a beam or a floor and having it deflect 6 inches. Well, that's not going to be very good. So we've got to obviously design for that. But if it's a vibration issue, maybe there's another clever way using mechanical components, a smarter structure, if you will, to counter vibration problems. So, but definitely appreciate, we call it sustainability or green engineering thinking in the direction of using less material. That it's an absolute requirement.
Okay, looks like there is another question. When will IISC and AISCE 7 stop stress-only approach and use deflection and strength approach like AISCE 40?
Let me understand. I'm going to ask you a question just to see if you think this is what the user's after. So the question I'm interpreting this is, when will AISC sort of give up on allowable strength design and just take on an ultimate strength design approach? Is that the question?
Yeah.
Yeah. We continue to this day. In fact, I am on a phone call this afternoon with ASCE 7 to continue this conversation. I'm an advocate for simplifying the design process. And one way to do this is to limit the number of opportunities and be consistent with the rest of the world on how you design structures. The rest of the world uses ultimate strength design, and it's absolutely time for AISC to move in that direction. There is such a realistic possibility. The way we do connections is that we subcontract connections, and it has to be absolutely clear to the subcontractor designing those connections what loads they're receiving. Are they receiving ultimate strength loads or allowable strength to design loads?
Yes.
And if a mistake is made there, and we are pretty sure mistakes have been made. I mean, you just can't live in this environment and not have a mistake. The odds are just too high. It's going to be quite problematic if you use the wrong loads. I think it's in everyone's best interest to get there. But at the same time, our profession in steel design has been quite heavily based on allowable strength design. So making that transition is not easy for our profession, but it is well overdue. And I really hope that at least by 2028, with that specification, we can start to make headway. Maybe allowable strength design will find its way in an appendix, and then by the next 6 years, it'll finally no longer be with us. Now, one very interesting development is right now, ASCE 7 is considering doing something that I would call the great equalizer. And right now, if you go into our building code, our ASCE 7 code, LRFD load combinations are provided and ASD load combinations are provided. So we have two separate sets of combinations that are not necessarily aligned in providing equal levels of reliability. So one thing that they are considering doing, and they'll be voting on in the upcoming months, is to only in the building code provide the ultimate strength or the LRFD factored load combinations. Then when it comes to allowable strength, which they will continue to permit, what they're going to say is the load combinations you are to design by should be the LRFD load combinations divided by 1.5. This is huge. This is what I call the great equalizer, because our factors of safety, our resistance factor, our phi factor for LRFD, and our omega factor for ASD actually have a ratio of 1.5. So if you do this, you will not end up with any difference in the design, whether you do LRFD or ASD. And perhaps that will be, a big step towards the profession realizing there's nothing to be gained in ASD or LRFD, but let's just take on LRFD. So I think I'm with the person asking the question that we are well over time, in doing that. And I look forward. I mean, even from an educational standpoint, I marvel at folks at other universities outside of the U.S. They go down ultimate strength route, and that's their whole course. At the the U.S. universities, we sort of have to focus on making sure the engineers are up to speed, or our future engineers in both LRFD and ASD. So we have this second level that is really not needed in our education system. So we'll see where it goes, but fingers crossed we will start. And I really feel like we're starting to make the turn on this. And I've said this before, but now I really feel like it. I can see, what's going on at AIC and ASCE 7. But there are other industries like timber. Well, clearly concrete is all ultimate strength, so there's nothing there. But timber is going to be many generations out from moving to LRFD. So if you have structures that use both steel and timber, the steel folks tend to like to use the ASD because it's consistent with how they're designing the timber portion of the structure. But it's just some thoughts there. Okay. Thank you for the question.
So thank you, Ron. Thank you so much. I would like to invite Professor Ron. Thank you so much for giving this wonderful talk. And I would like to invite Professor Ron for the backstage. And with this one, we will complete this day's session, and the fourth keynote is completed. I look forward to meeting you all tomorrow with the fifth keynote session by Professor K.H. Tan from Nanyang Technological University, starting at 9:30 a.m. Indian time. Thank you all. Professor Ron, you can come to the backstage. We will be